Hello, in this lecture, we are going to discuss an important consequence of Laplace's equation. Okay, so Laplace's equation told us that del square b equal to 0, and we were discussing in previous lectures some interesting consequences. And one of the interesting consequences was that the solution for this Laplace's equation, which happens to be which we call as harmonic function, this particular harmonic function does not admit any local maximum or minimum. Any local maximum or minimum, maxima and minima. And this particular result leads us to an important theorem in electrostatics, which is called as Earnshaw's theorem. So immediate consequence of Laplace's equation, an immediate consequence of Laplace's equation of Laplace's equation solution, like not having a minimum, not having a local minimum, is that a charge cannot be held charge cannot be held at a stable equilibrium at a stable equilibrium uh, by by electrostatic forces alone, by electrostatic forces all alone. That implies that if I need to find a point of stable equilibrium, a point at stable equilibrium cannot be due to the electrostatic forces alone. That is, if if I have to keep a test charge. Why test charge? Because we want to probe that in the space, if there is a stable equilibrium, how to probe that particular stable equilibrium? I will have to place a test charge. So if I have to place a test charge in a space, it cannot be at equilibrium. It cannot be at equilibrium. It cannot be at equilibrium all alone by electrostatic forces, all alone by electrostatic forces. Rather, I would need uh, like forces other than that. That I would need like gravitational force or possibly magnetostatic forces, etc. So all alone by electrostatic forces, we cannot have a stable equilibrium in a space. Okay, magnetostatic force, and that particular space must not contain the charge. This test charge we are bringing in order to probe that particular point in the space is at a stable equilibrium. So understand my point. So for example, how to prove this particular thing? So for example, let us consider that there are charges. I'm just considering a few charges here, like Q1, Q2, Q3, Q4, Q5, and Q6. So let us consider that there are all these charges, and let us consider that there is a point in the space. There's a point in the space. Let us say that is some x. Let us keep that in general, and let us keep that as some x. So I'm keeping it as some x. Okay. So like these are some. If you can generalize it, you can keep n charges, and all. I'll say the consider, and then there are many charges all around. Why should I take only 6 charges? There are in like n charges. Consider n charges: Q1, Q2, Q3, Qn to be n charges. This is an elementary proof that I'm giving. Then I'll give you the proof, which is quite that you can understand from your Laplace's equation. So eventually I will do this only. That is, I will prove that from the consequence of Laplace's equation, a charge cannot be held at a stable equilibrium by electrostatic forces alone. But eventually I will make a very simple proof that is from your standard 12. So for example, if I consider a set of n charges, and these are n fixed point charges, and in a vacuum, an electric field is produced by these charges. Electric field as a function of x is produced in these charges. We want to find a point, let's say x naught, in the space such that if a test charge q is placed there, if test charge q naught, I will say, is placed there, it remains at static equilibrium. It remains at static equilibrium. So understand what I want to say. I'm saying that there are only charges. So if at all this is the point where we want to see ki there's a stable equilibrium, so what I need to bring a test charge. So I'll bring a test charge q naught, and q naught tends to be very limiting, very small, so that it does not perturb the other field. So for example, if I bring this charge q naught, will it remain at static equilibrium? The question is that if q naught is there, it is under the influence of only electrostatic forces. So if at all it has to remain at equilibrium, it has to violate the Earnshaw's theorem. What Earnshaw's theorem says, that a charge cannot be held at stable equilibrium all alone by the electrostatic forces. So let us see whether this happens or not. So one thing that you know from your from very initial days, that a point is said to be static equilibrium if from that point, if certain, you can say, certain displacement is made, and then the force should be in that restoring direction. So for example, if I say that this is a point of static equilibrium, if I displace my particle from x naught to x naught plus delta x, then my force must point in this direction. Force due to certain, like here it is due to the electrostatic reasons. So here it is electrostatic force. So restoring force must act in order to restore it back to the mean position. And if I displace it from here, then again restoring force should act in this direction. Then I would say that my point x naught is a stable equilibrium point. And also understand that at this particular point, your force vector must be zero. Your force vector must be zero. So if I bring my test charge, at, if test charge q naught is brought at let's say x naught, then the first thing is that q naught times electric field at x naught must be zero. The first thing is that q naught times electric field x naught must be zero. And second thing is that if I make small displacements, so for small displacements, let's say small displacement is delta x around x naught. So if I make a small displacement of delta x around x naught, my q, that is force, that is electric field, x naught plus delta x must point towards x naught, must point towards x naught. I think it is clear. Okay, and understand that x naught did not have any, like if I want to make a Gaussian surface, did not have any charge. And just bringing this charge q naught in order to say that what kind of forces it will have, like what kind of forces it will be subjected to. So I need to find whether this particular point x naught is a stable equilibrium or not. For that, I'm bringing a test charge. Otherwise, remember, this particular space did not contain any charge. Whatever charges are there, they're like I have denoted them by these points. Is that clear? What I would do, I would simply make a Gaussian surface. So these are my charges. Again, I'm making the figure. These are my charges, different other charges. Like these are n charges which are placed, and these are all n charges placed. I'm writing q1, q2, q3, q4, q5, q6, q7, q8, and then this is q9. There's all these charges are there, and then this is qn. And here is a point which is x naught. Here is a point which is x naught. So what I'll do, I'll make a Gaussian surface around it. I'll make a Gaussian surface around it. Is that clear? So I'll make a Gaussian surface around it. So this is my Gaussian surface. Okay. Now, because of these forces, there would be some field inside, isn't it? Because of these charges, there would be some force. There would be some field inside, isn't it? not because of the charge q naught. Like charge q naught does not have its own field, but rather it will be affected by the presence of all these charges. Because of these all charges, there would be some field. Okay, and this particular field at x naught must be must act inwards. This is what is suggested. See, for example, if I move from x naught to delta x, x naught plus delta x, what is happening? My electric field must be such that it can push my charge particle towards x naught. So if I'm taking the case of q naught being positive, if I'm taking the case of q naught being positive, if my electric field pushes it away, then it does not make sense. Then it cannot be a stable equilibrium. So understand that my E vector about x naught must be inwards. Only if it is inwards, only then it may be of the restoring nature. So what does it imply? It implies that if I make this kind of Gaussian surface, my integral E vector dot ds vector must be less than 0. Why less than 0? Because your electric field is inward, your ds is outside, so E vector dot ds will be 0. And also understand, if this is a Gaussian spherical surface, then this particular thing can be written as del dot E vector d tau over this volume V. So if the volume of the Gaussian surface is V, which is bounded by surface S, then this particular thing by Gauss divergence theorem will be equal to del dot V vector d tau, and this will be equal to net charge enclosed divided by epsilon naught. And if it is the case, then net charge enclosed divided by epsilon naught should be 0. Okay. So understand, this cannot be negative, because this is where we arrive at a contradiction. Why we arrive at a contradiction? Because we know that our assumption was that x naught is a point where there was no field, where there was no charge. Understand, this charge is the test charge that we are bringing to probe it. For example, in order to probe, we are bringing this charge q naught. And if I brought this charge q naught, I'm in a position to say that my E dot ds would be negative. Only then I can say that that if this particular point is a point of stable equilibrium. How to understand this? So what we do, we bring a test charge q naught, and we see that if this is a test charge q naught, and if this is a point of stable equilibrium, then q naught once displaced should come back to this particular point, isn't it? If it comes back to this particular point, what does it imply? It implies that the net electric field due to all these points, understand, this electric field is not due to this q naught. This electric field is due to all these other charges. It should be in the restoring direction. If it is in the restoring direction, then this Gaussian spherical surface, inside this Gaussian spherical surface, your E dot ds must be negative. And if your E dot ds is negative, then your q enclosed divided by epsilon must be 0. So which is in a contradiction to our initial assumption, where x naught was a point where there was no charge. And also understand, q naught does not count. Does not count, as it is the test charge. In order to prove I'm doing it. It is the test charge है. Just in order to understand कि electric field inward है कि नहीं है, I have placed this charge unit. Understand this point. So it is the test charge, and the electric field is not due to q naught. Rather, it is due to the all other surrounding charges. Overall, we arrive at a contradiction. And what is a contradiction? We asserted that this particular x naught was our stable equilibrium. So again, I'm coming back to the problem. What we asserted initially, we asserted that x naught is a stable equilibrium. If x naught is a stable equilibrium, two things it is going to follow. One, that this net electric field should be 0. A q naught into electric field x naught should be 0. And for small displacement around x naught, q times electric field x naught plus delta x must point towards inwards. That is, if I say that if in order to probe it, I brought a test charge, and if I bring a test charge here, if I displace it slightly, electric field must act inwards. So total overall, you should understand your electric field must act inwards. So electric field at around x naught must act inward. So if I write E dot ds, so if your electric field is acting inward, your spherical surface, this particular ds vector will be outwards. Overall, E dot ds would be negative. If E dot ds is negative, that implies del dot E vector Like the divergence of E vector should be divergence of E vector theta integral. This is the volume integral must be, which is equal to Q enclosed upon epsilon, must be negative. If it is negative, then this is again at a contradiction, because you understand your x naught was a point where there were no charges. How can it be negative? There were no charges. Q naught does not count. Understand, Q naught does not count because Q naught is a test charge that we brought from somewhere, so that in order to understand what is the what is the nature of electric field. So you understand the electric field's nature is restoring. Only then you can have a stable equilibrium. So this is in contradiction to the assumption that your x naught is a point of stable equilibrium. Hence, you cannot have a point of stable equilibrium. So hence, you can say that you cannot have a point of stable equilibrium under the influence of electrostatic forces alone. Under the forces of electrostatic forces alone. Another way to express this is in a very simple manner, and that I think seems a better thing to do. So for example, again, let us consider this point, and there are infinitely there are n different charges placed here. So there are n charges placed here. Is that clear? So there are n charges placed here. So because of these n charges, Q1, Q2, Q3, so on and so forth, Q5, Q6, Qn, there would be some electric field. And let's say this is the point of interest, which I placed x naught. So in this particular region R, there is no such charge. So I can write that here in this particular region, what should I say? Region S. In region S, in region S, in region S, you can say that one can say that there are no charges present. So del square V must be equal to 0. And this potential will be brought about by the distribution of these n charges around. I mean, these all n charges, after all, would give rise to certain potential in this region S. So del square V equal to 0. And if del square V equal to 0, we know that V does not tolerate any maximum or minimum, any local maximum or minimum. Now, in order to understand stable equilibrium, again, we have to bring a test charge. So if I bring a test charge at this particular point, Q naught into V, this will become the potential energy of the test charge. And if I'm saying that if this is a point of stable equilibrium, then if I bring a test charge, then it must be at a stable equilibrium. That implies your potential energy of that test charge, potential energy of the test charge Q naught must be minimum. And if it is minimum, then you should understand that that Q naught into V must be minimum. This is what it means, must be minimum. Forget about Q naught. Just understand Q naught is a scalar thing. It implies V must have a local minimum at x naught, which is a point inside the region S, a region S, and which indeed is a contradiction to the to the to the uh, to the Laplace's equation, because we know that the solution for the Laplace's equation, which is a harmonic function, cannot tolerate a local maximum or minimum. So at x naught, you cannot have a local minimum. So here we arrive again at a contradiction from the consideration of Laplace's equation. Please don't get confused with this Q naught. I mean, there are people who would say that this Q naught if placed, then how can you say this is a chargeless region? I'm not saying that I'm placing this Q naught in order to make a judgment about potential energy. Overall, understand this is a chargeless region. So if you do not have a charge, then del square V would be 0. If del square V is 0, then V does not tolerate any local maximum or minimum. And if it is the case, then understand my point that if I just bring a charge Q naught in order to make some sort of understanding, if I bring this charge Q naught, if it is this particular point x naught is a stable equilibrium, then this charge Q naught, when placed here, the potential energy should be minimum. So what is potential energy? Potential energy is Q naught into V. It implies your V must have a local minimum at x naught, and which indeed is at a contradiction with the Laplace's equation. So overall, understand all the equilibrium points in electrostatics are rather unstable. Or you can say that they are saddle points. They are saddle points. They cannot be local minimum or maximum. So this is an important assertion, and there are lot many confusions that this particular lecture can bring about. Kindly let me know about whatever confusions you have in your comment section, and I'll try to respond you with a better reply or sort of reply. I hope that this solves your problem. This is a fourth lecture to the series of Introduction to the Laplace's equation, and this is one of the important consequences of the Laplace's equation. One of the argument, this is Richard P. Feynman's argument, which I have written, which is like very basic kind of argument, and this is an argument that you'll find uh, in most of the books, like advanced textbooks, like probably Griffith or books like that. Okay. So understand these are the things that I wanted to convey. I hope you got my point. Take care.